So in this video, we will briefly talk about analysis of variance. So, or we may call it ANOVA. So basically, what is ANOVA? Basically, let's say we have problem. So we would like to figure out a reliable treatment method to analyze the days it took for the patients to be cured. We can use a statistical technique which can compare these three treatment samples and depict how different these samples are from one another. So in such technique, usually compares the samples on the basis of their means, and this is what we call ANOVA. Which ANOVA is basically a statistical technique that is used to check if the means of two or more groups are significantly different from each other. And this ANOVA also checks the impact of one or more factors by comparing the mean of different samples. So here, when we have only two samples, t-test and ANOVA would give basically similar result. However, if we have more than two samples, if we are using t-test or t-statistics, it would not be as reliable as ANOVA. And here, where ANOVA usually used, it is commonly used to test the hypothesis of equality between two variances and among different means. So the mean, it doesn't have to be same level. Also, it is one of the standard, and it's very useful technique for experiments in the field of psychological, sociology, education, commerce, and several other disciplines. And this techniques is an advanced techniques for experimental treatment of testing differences among all the means, which is not possible in the case of t-test or t-statistics. And so we have several terminologies that you might need to know in order to understand ANOVA. So here we have grand mean. Grand mean basically is a simple or arithmetic average of a range of values. Here mean. So there are two kinds of means that we use in ANOVA. So for ANOVA calculation, we separate means from regular means, and then we have grand means. The grand mean is the mean of the sample means. So the mean of our previously means of all observation combined. So it's actually irrespective of the sample. So the next one you already learned in the previous chapter, we have hypothesis. So considering here this hypothesis is basically the same. We have null hypothesis, which is the original hypothesis, and also the alternate hypothesis. In ANOVA, here the null hypothesis is valid when all the sample means are equal or they don't have any significant difference. Thus, they can be considered as a part of a larger set of the population. On the other hand, the alternate hypothesis is valid when at least one of the sample means is different from the rest of the sample means. So here you have the representation of this null hypothesis and alternate hypothesis, where mu L and mu M belong to any two sample means out of all the samples considered for the test. So in other words, the null hypothesis states that all the sample means are equal, or the factor did not have any significant effect on the result, whereas the alternate hypothesis states that at least one of the sample means is different from the other means. So we have varies of means, but we still can't tell which one specifically. For that, we will use other method that we will discuss later in this video. So the other thing is a between group variability. So consider the distribution of the two samples we have here. These two samples, as these samples overlap, their individual means won't differ by a great margin. So hence, the difference between their individual means and the grand mean won't be significant enough. Now consider the other sample here, where we have a big margin. As the sample differ from each other by a quite large margin, their individual means would also be differ. The difference between the individual means and grand mean would therefore also be significant. And here, such variability between the distribution called between group variability. It also refers to variance between the distribution of individual groups or maybe levels, as the values within each group are different. Here, each sample is looked at, and the difference between its mean and grand mean is calculated to further calculate the variability. If the distribution overlap or it's close, then the grand mean will be similar to the individual means, whereas if the distribution are far apart, the difference between means and grand mean would be large. So for example, here we will try to calculate. We can calculate the between group variability as we calculate just like the standard deviation. Given the sample means and grand means, we can calculate it as like this. This one is just the means, and this xg is the grand mean. We also maybe want to weigh each squared deviation by the size of the sample. In other words, a deviation is given greater weight if it's from a larger sample. Hence, we will multiply each squared deviation by each sample size and add them up. And this will be called as the sum squares for between group variability, or we can say SS between. And there is one more thing that we might want to do, is to derive a good measure of between variability. Again, recall how we calculate the sample for standard deviation. We may find the sum of each squared deviation and divide it by the degrees of freedom. For our between group variability, we will find each squared deviation, weight them by their sample size, sum them up, and then divide by the degrees of freedom, or df between, which in the case of between group variability is the number of sample means, or k minus 1 here. We have k minus 1. Okay, so another thing is we have previously we have between group variability. So the opposite of between group variability is within group variability. So consider we have this example, distribution of 3 samples, as the spread of the variability of each samples is increased. Their distribution overlap and they become part of a big population. Now consider another distribution of the same 3 sample with less variability. Although the means of samples are similar here, this one and this one have similar means, they seem to belong to different populations. Such variation within a sample are denoted by within group variation. It is referred to a variation caused by differences within individual groups or level, as not all the values within each group are the same. So each sample is looked at on its own, and variability between the individual points in the sample is calculated. So in other words, no interaction between samples are considered. And we can always measure the within group variability by looking at how much each value in each sample differs from its respective sample mean. So first step, we will take the squared deviation of each value from its respective sample mean and add them up. This is the sum square for within group variability, or we can say SS within. And please note that this I value is the value from the sample. First sample, we have first sample, second sample, and k sample. Okay, so like between group variability, we then divide the sum of squared deviation by the degrees of freedom to find a less biased estimator for the average squared deviation, and this essentially for the average size square from the figure we presented here. Again, this quotient is called the mean square, but for within group variability, ms within, we say it ms within here, ms within. This time the degrees of freedom is the sum of the sample size n minus the number of the sample, or k. So another way to look at the degrees of freedom is that we have the total number of values n and subtract 1 for each sample. Another thing is F statistic. So the statistic which measures if the means of different samples are significantly different or not. We call it F ratio. So lower the F ratio is more similar or the sample means. In that case, we cannot reject the null hypothesis. We use this F ratio using this equation with variability between groups and variability within groups. So this formula is pretty intuitive. The numerator term in the F statistics calculation defines the between group variability. As we hear earlier, as between group variability increases, sample means grow further apart from each other. In other words, the samples are more probable to be belonging to totally different population. So this F statistic calculated here is compared with the F critical value for making a conclusion in terms of our example earlier. If the value of calculated F statistics is more than F critical value for a specific alpha divided by significance level, alpha or significance level, then we reject the null hypothesis and we can say that the treatment had a significant effect. So basically, there is only one critical region in the right tail shown in previous here. If the F statistic lands in the critical region, we can conclude that the means are significantly different and we may reject the null hypothesis. Again, we have to find the critical value to determine the cutoff for the critical region. We will use, probably, we need to use the F table for this purpose. So we also need to take a look at different F values for each alpha or significance level, because F critical value is a function of two things, which is df within and df between. Terminologies that might be useful for this ANOVA is post hoc test. So it is used to determine which mean or group of means is or are significantly different from the other, but we cannot tell which one is different. We just can say that this group is different, and depending upon the research design or question, we have several values here. Okay, so next to the first kind of ANOVA, which is a one-way ANOVA. So basically, one-way ANOVA is only have one vector that is computed. It is usually called as a single classification of ANOVA. Here, for example, here we have three groups are selected for an experimental treatment on one factor. This one factor define which the variance, this evaluation of performance is of three groups on the basis of three attitude scales. In this one-way ANOVA, the total variance is equal to the variance within groups and variance between groups. So we have several data required for this one-way ANOVA. At least we have three independent groups, which is significantly different from one another. And we have only one independent variable. It could used to for factoring or grouping variable. And here are the basic steps how we calculate these ANOVA or analysis of variance. First step is to state the null and alternative hypothesis. State the alpha, calculate the degrees of freedom, state the decision rule, and then calculate the statistic. Calculating test statistics mainly consists of three things, which is calculating the variance between samples, variance within the samples, and also calculating the F statistic. So we have here H0 or null hypothesis, state the alpha, and calculate the test statistic. And after that, we may calculate how to calculate the variance between and variance within samples. We have you can check the calculation here later on to check the how we can calculate. For variance between, we use this MSC, and for variance within, we use this MSE. Okay, so let's take a look on the example how we can calculate the ANOVA for this three kind of samples. So we have here three samples are obtained within from normal population with equal variance. So we need to test the hypothesis that sample means are equal. First, we are grouping into three groups of sample, and then we measure the means of the samples. First mean is 10, second mean 8, and the third mean is 12. And then we calculate the grand average. The grand average, we just sum the means divided by total means, which is 3. We have a grand average of 10. So we first make the null hypothesis. Here, no significant difference in the means of three samples. And then second step, we state the alpha value. Here in this example, we state the alpha value is 0.05, and then we calculate the degrees of freedom. We have to remember the degrees of freedom, k minus 1. K is the total groups of samples, which is 3 minus 1 equals to 2. And the n minus k, we have n 15 population from the population, 3 groups, each 5, so it's total 15, minus k 3, so 2 and 12. And then we need to state also the decision rule. So the table value of f at 5% level of significance for DF 2 and 12 is 3.88. So the calculated value has to be, if the calculated value of f is larger than 3.88, the null hypothesis will be rejected. And don't forget, we need to calculate the test statistic. So how to calculate it? First, we need to calculate the variance between samples, which is, we have these three means, sum of the square between samples of SSC, we get this value 40, and the calculation of mean sum of square between sample MSC, is 40 divided by k minus 1 divided by 2, so it's 20. K is number of sample, and n is total number of observation. So we have the variance between samples. Now we have to calculate the variance within samples. Here are the calculation. So we got the MSE values of 60 divided by 12, which is equal to 5. So after that, we need to check the F ratio. The F ratio is equal to 4. So based on this F value at 5% level of significance for DF2 and 12 is 3.88. The calculated value of F, which is 4, is larger than the table value of 3.88. So hence we can say that the null hypothesis is rejected. And there is a significant, which means there is a significant difference in the sample means. So it was the hard way to calculate. We also have the shortcut method. So by shortcut method, we can calculate it like this. Using this table to calculate total sum of observation 150 and given the correction, and total sum squares, we have this value that we have for one-way ANOVA. Let's move forward. We have also two-way ANOVA. Here in two-way ANOVA, there is more than one experimental factor and one or more control factors. In case of the previous one-way ANOVA, the 3 attitude scales for the test is performance are experimental factor, whereas the examiner is the control factor. If the tests are concluded by 2 examiner, so the overall factors will be 3 multiplied by 2, which is equal to 6. And this two-way ANOVA is also called double classification ANOVA. This procedure can be used for the application of three-way or larger class of ANOVA. Say for example, in this two-way ANOVA, in the previous one-way ANOVA, we have one independent factor. Let's say about music treatment, which will helpful improving the test results of the students. However, we only see this when the students are at similar age. What if we add more factors? Like, what if the treatment was to affect different age groups of students in different ways? Or maybe the treatment had varying effects depending upon the teacher who taught in the class. So, moreover, in one factor, we cannot answer that more factor. So for such cases, when the outcome or dependent variable is affected by 2 or more independent variable or factors, we use a slightly this modified technique. For example, in this one-way, in the previous one-way test, we found that the group subjected to, let's say, variable music and no music at all perform more or less equal. It means that the variable music treatment did not have any significant effect on the students. So while performing two-way ANOVA, we will not consider the previously variable music treatment for simplicity of calculation. Rather, a new factor, age, will be introduced to find out how the treatment performs when applied to students of different age groups. And this time we have a more complex data sets. For example, here we have two factor class group and age group with 2 and 3 levels respectively. So we now have at least 6 different groups of students based on the different permutation of class group and age groups, and each different group has a sample size of, let's say, 5 students. There are several questions that two-way ANOVA can answer about our new data sets here. Is music treatment the main factor affecting performance? Or in other words, do groups subjected to different music differ significantly in their test performance? Is the age the main factor affecting the performance? Or in other words, do students of different age differ significantly in their test performance? Or also, is there a significant interaction between the factors? And the next question will be, can any differences in one factor be found within another factor? This two-way ANOVA tells us about the main effect and the interaction effect. The main effect is similar to one-way ANOVA, where the effect, let's say, of music and age would be measured separately, whereas the interaction effect is the one where both music and age are considered at the same time. That's why a two-way ANOVA can have up to 3 hypotheses, which may be, let's say, hypothesis 1, hypothesis 2, and hypothesis 3. And F statistic is computed for each hypothesis we are testing. Okay, here we also have the data required for the two-way ANOVA. When two independent variables, or it could be nominal or categorical, have an effect on one dependent variable, ordinal or ratio measurement scale. So we need to compare relative influence on dependent variable, examine interaction, and just as we had sums of squares and mean squares in one way, we also have the same here in two-way ANOVA. So we also need, I mentioned earlier about 3 null hypotheses. Means of observation grouped by one factor are same. Means of observation grouped by the other factor are also the same. And also there is no interaction between the two factors. The interaction test tells whether the effect on one factor depend on the other factor. So let's see here we have an example here. Let's say a farmer applied 3 types of fertilizer on 4 separate plots. The figure on yield per acres are tabulated on the table here. Please find out if the plots are materially different in fertility, as also if the 3 fertilizer make any material difference in yield. Here we have the several parameters: nitrogen, potash, phosphate, and we total the types of yield and types of fertilizer. We have here 3 types of fertilizer and 4 types of plots. we have also the squared data for each yield. Okay, so how to solve this? First, we have to make a null hypothesis. Let us take the hypothesis that all plots are not significantly differ in fertility, and all the fertilizer are not significantly differ in yields. This will be the row and the plot will be the column. So step 2, we have to make the correlation factor. The correlation factor equals to sigma x squared divided by n, which is 588. And step 3, we sum the square total, is sigma x squared minus c. So we have here sigma x squared equal to 624 minus 588, which is equal to 36. And step 4, we need to sum square between columns. The value is 18. Step 5, we have to sum square between rows, and the value is 8. Followed by sum square within groups, which is 10. And then we have to calculate the degree of freedom. For total sum square, the degree of freedom equal to 11. There we have 4 degree of freedom. Sum of square between columns, between rows, and within groups. We have 11, 3, 2, and 6. So in the next step, we have to put it in the table. And the last step, it should be step 9, we have to interpret this value. Here, we have to see from the column-wise analysis, and also row-wise analysis. So from the computed value of f 3.6 is less than the table value of 8.94. Hence, the null hypothesis is accepted, which means the mean plots are not significantly differ in fertility. So let's take a look at row-wise analysis. So the calculated value f equals to 2.4, which is less than the table value of 19.33 here. So the null hypothesis will be accepted, which means the fertilizer are alike so far for productivity concern. Okay, so we already see the advantages, the uses of ANOVA, one way or two ways. But also here, as for statistics, because statistics never give an exact value, always estimation. So we have a lot of limitation here for ANOVA. For example, here it is difficult to analyze ANOVA under strict assumptions regarding the nature of the data, and it is also not so helpful in comparison with t-test or t-statistic, that there is no special interpretation of the significance of two means. It is not always easy to interpret the case of multiple interaction and their significance level. It also has a fixed and difficult set for designing experiments for the researcher. And also requirement of post hoc ANOVA t-test for further testing. And sometimes it time consuming, and also time requires knowledge and skill for solving numerical problem. It also provides no additional information as compared to the t-test or t-statistics. Right, so here we have, unlike the previous chapter, we we have only two exercise here. Please do the exercise and don't forget to submit at AMAS on time. As usual, we have 1 week for submission. I will open the submission today at from 1 p.m. until next week. Also will be closed at 1 p.m. and next week will be 7th of May. Please pay attention to the submission deadline. Thank you very much for your kind attention and see you in the next chapter. Thank you.